All right. So before Christmas, I know that's a long time ago now, okay, but before Christmas, we talked about energy transfers in a global system, okay, and that was before we started the climatogram activity. So the things we talked about when we talked about energy transfers were that we talked about conduction, convection, and radiation. Okay? Those are the three methods by which energy can be transferred within a global system. Right? Which one is most important for getting energy to Earth? Radiation. Okay, it's coming to the Earth from the sun and light. Okay, what's the one that's most important for transferring it on Earth or around Earth? Convection. Okay, so today we're going to be focusing on how convection works in a global system by looking at the wind patterns that we see develop on Earth. All right, a couple other things we talked about in regard to this. Okay, we talked about albedo, which is also going to be kind of part of what we talk about today. Albedo is the reflectivity of the Earth's surface. A high albedo means it's very highly reflective. A low albedo means it's very absorbing, okay, and can absorb a lot of the energy from the sun. Is that ringing a bell for everybody from before Christmas? Okay. All right, so those are kind of just quick review of the things that we had talked about there. Okay, so what we're looking at today, okay, is how energy gets distributed on Earth. Okay, we're going to look at the role that winds play in distributing energy. Okay, we're going to talk about something called the Coriolis Effect. Okay, and how it causes the wind patterns that we see. Okay, on Earth, and this is probably the most important point. Okay, recognize that these wind patterns we're going to talk about are the product of both convection and the Earth's rotation, and the Earth's rotation has to do with the Coriolis effect. How many people have heard of the Coriolis effect before? Okay, one or two. It's usually new. Okay. All right, questions so far? Right. Okay, so the Earth's atmosphere is always moving. Okay, there's never a point where the air on Earth is stationary. Right? Just because it's not windy out doesn't mean the air is not moving. All right, everyone okay with that idea? The reason that the air moves is to equalize things. Okay, most of the time it's trying to equalize temperature and pressure. Right, so both of those things can cause winds. If we're getting a Chinook, it's equalizing pressure. There's a pressure difference that's being created, okay, that's causing that wind to flow, right? Which is why a lot of people get headaches, okay, when Chinooks come. There's such a radical change in atmospheric pressure, okay, when they come that sometimes people are sensitive to that and it can give them headaches or migraines and things like that, okay? So one of the causes of wind is pressure, okay? The other is temperature. We're going to focus more on the temperature part of it today because that's also a big part of why wind happens, okay? Or just wind is happening to help to obey the second law of thermodynamics, that energy flows from hot to cold, right? And so the wind patterns are set up in that way. They're transferring energy around the Earth. If that didn't happen, okay, then the equator would be a like burnt wasteland, and the poles would be absolutely frozen. There'd be two like narrow bands on Earth, okay, where life could possibly exist. Thankfully, that's not the case. The atmosphere is always moving and transferring that energy around. Okay? All right, so if we're looking at the Earth, okay, the Earth spins this direction. Okay, use a color you can see. Okay, the Earth spins this direction, which is why the sun rises in the east. If it's spinning this way, we get into the light east first. Okay, everyone follow? And then we rotate under the sun. Okay, and when we get over here, we look to the west and see the sun go down. All right, so that's why the sun rises in the east and sets in the west. All right, that causes us to feel like there's atmospheric movement because the atmosphere and the Earth don't move together as one piece. Okay, they do to an extent, but not completely. The Earth can actually spin under its atmosphere. All right, and so it's the equivalent of like, so we're standing on the Earth's surface and it's spinning under its atmosphere, essentially pushing us through the air. Right? We don't notice that so much because it's not like the atmosphere is standing still. The atmosphere is moving a bit as well, so we don't really notice it. It's not like sticking your head out a window of a moving car. Right? It's not like that fast, okay? But we are moving through the Earth's atmosphere all the time due to the fact that the Earth is rotating. Okay, and so that causes sort of directional wind patterns that we're going to talk about. Okay, so nature doesn't like imbalance or inequity. Okay, we know that from the second law of thermodynamics. Energy is always flowing from hot to cold in an attempt to equalize. Okay, variations in temperature create variations in pressure. Okay, as a result, air moves from areas of high pressure to low. Okay, as well as from hot to cold. Okay, and we sense that movement as wind. Okay, the wind in turn transports heat, energy, and moisture. That's really important. Okay, we talked about that in lesson 3 as well. Okay, where we were talking about the the role of latent heat. How many people remember that term? Sound familiar? Okay, so remember that latent heat is the heat that's carried by water vapor. All right, at the equator is where the majority of water vapor is created, essentially, where water evaporates. Okay, the movement of the Earth's atmosphere causes that water vapor to move from the equator towards the poles, and it carries with it all the stored energy that it gained as a result of changing state from liquid to gas. Right? When it gets to more northerly areas, it condenses and releases that latent heat. Okay, in other words, transferring energy from the equator to more northerly or southerly areas, okay, through that mechanism. Okay, it's actually a fairly large player in terms of how much energy it transfers globally. All right, so wind in turn transports heat energy and moisture, okay, influencing global climate. The jet stream, okay, how many people have heard of the jet stream? At least heard the term. Okay, so the jet stream is a high altitude, very high speed wind mechanism. It influences our weather a lot, but it also helps to transfer latent heat as well as sensible heat around the globe. Even though it's at a very high altitude, it can influence the movement of air at lower altitudes. Right? So the jet stream, okay, sometimes you see it, the weathermen or whether the meteorologists will show it on the map, okay, and it kind of looks, it has a different shape all the time. This is about as radical a shape as the jet stream could show, okay. Most of the time the jet stream just kind of looks like this, okay. Now, the location of the jet stream is influenced by pressure. If there's areas of high pressure and low pressure, they can push the jet stream into different places, okay, and make it look kind of wonky like it does on this picture here. Okay, so what happens is if the jet stream is moving like it is in this picture here, so it's moving this direction, it's going over this high pressure area where it's warm and dry. Okay, but it wants to rotate around that high pressure area like this, and there's all this cold air right here. Okay, and so that cold air, okay, pushes the jet stream this way, and now what we're getting is an interaction of these two air masses. Okay, they'll push down this direction and they'll cause really unsettled weather, okay, anywhere where they kind of meet. Okay, because they're two different types of air masses. One is hot and dry, the other is cold and wet. Okay, and so they're going to create fairly unsettled, like a thunderstorm, or things like that. Okay, so in this case here, okay, we've got this jet stream then going back out to sea, okay, and then coming back through this way, okay, and it's essentially going to block that cold air from going any further south, again causing, okay, this interaction between tropical air and cold air, okay, where you could have unsettled weather. All right, but the jet stream can really move air masses long distances north and south, as well as east and west. Okay, the most common way that we hear about the jet stream is that jets can use it to save fuel. All right, lots of pilots will try and get into the jet stream if they're flying from west to east, because that's usually the way it blows. Okay, and that they can get into that jet stream and it'll save them fuel because it's essentially a big tailwind and pushing them along. If they're going the other way, then they want to avoid it like the plague. Okay, sometimes your plane will pass across the jet stream. How will you feel then? Turbulence, yeah, okay, it's really unsettled. It's a high-speed wind mechanism, okay, and so pilots will change altitude to try and avoid it whenever they can. Right, so it's evidence that it is there, okay, and it is doing this particular thing. All right, so the role of the jet stream is to help transfer heat, energy, and moisture, which we're going to also say is latent heat. Okay, so that's its big job. So if I gave you a question on an exam, like, okay, can you describe some of the ways in which energy is transferred on Earth? The jet stream should be one of those methods, okay? And you would explain, here's how it does that, okay? It can move air masses around, it can force latent heat to move around, okay? And that's important. All right, everybody okay with what the jet stream is? Okay, here in Okotoks, which direction do the prevailing winds come from? From the west. Okay, most of the time from the southwest. Why is that? It's partially the mountains. I mean, that's where Chinooks come from, but most of our prevailing wind actually has to do with the way the air is cycling up and down vertically within the atmosphere and how the Earth is rotating underneath it. Okay, so prevailing winds, remember we said on the first slide, are the product of convection, okay, heat transfer vertically within the atmosphere, and the Earth's rotation, so rotating underneath a rotating column of air. So what happens is this, okay, in this diagram we see that at the equator, where most of the solar energy is received, okay, hot air is going to rise, okay, so we see that right here. Hot air is going to rise, and air from the north has to move in to replace it. Okay, that's how convection works. If all the air just rose, it would create a vacuum, right? And that can't happen. So as this air rises up, okay, air from further north comes in to replace it. That air is still fairly warm because we're talking about an equatorial area. Okay, so this air now has gone up into a higher altitude, okay, and it can't come back down, so it starts a rotational cycle. Okay, like so, called a convection current or a Hadley cell. Okay, so we'll just say that this is convection. All right, so that convection is going on. Meanwhile, the Earth is rotating this direction underneath it. So while air is doing this, the Earth is doing this, which makes it seem like the winds are coming from the northeast. So if you're at the equator, the prevailing winds are usually from the east to northeast, depending on where you are. Okay? And that's just the product of what's going on both vertically as well as horizontally. Okay, everyone with me so far? Okay, next level up is where we are. We're actually right at the transition area, okay, which is why we have the saying in Alberta, if you don't like the weather, wait 5 minutes. It's because we're actually in the transition area between the polar vortex and kind of the westerlies. Okay, so in this part of the world, the rotation is actually opposite. This warm air right here, I know I have it in blue, but it's warm air from the equator, is now finished its cycle, and it can actually jam itself underneath the air that's here because it's picked up speed because of this rotation. Okay, so it'll force itself underneath the air in this direction and move northwards. Okay, transferring the sensible heat and latent heat that it's picked up from the equator to this more northerly area. Right? Now, since again the Earth is rotating this way underneath that moving air, the wind appears to be deflected this way. Okay? And so we feel a southwesterly or westerly flow on these latitudes. Okay? When you get up near the pole, okay, the opposite is true. This hot air now has essentially lost all of its energy. Okay, it's transferred just about all of it to this kind of mid-latitude area. Okay, and so all we have is essentially the polar vortex or the polar easterlies. Okay, that are up here, and so they are always going to be a flow that is downwards. Okay, when they meet this slightly warmer air, that warmer air will rise. Okay, you still get a Hadley cell here, a convection current. Okay, but it's mostly cold. It's mostly just mechanical as opposed to energy driven. Okay, everyone all right with that? Okay, so that's how prevailing winds happen. We've got convection going on, hot air rising because the equator absorbs most of the energy. Okay, the Earth rotates underneath that rotation, okay, causing that perceived deflection of the wind. Okay. All right, now these winds here at the equator, okay, are typically called trade winds. Why are they called trade winds? Actually, no, but it's good. That's a good answer. It's not because they trade energy. It's because when we were first colonizing the New World, that's how we got over here. Okay, you would sail south to catch the easterly winds that would blow you across from Europe to the Americas. Okay, and then you would do all of your trading along the coast of the Americas and catch the westerlies to go back home. Right, so these were nicknamed the trade winds because they allowed trade to occur, okay, between the old world and the new world, okay, back in the early days. We're all right with that. Okay, so trade winds, probably a term you'll want to know. Sometimes it comes up in multiple choice questions, things like that. Okay, so trade winds are easterly okay? And obviously the westerlies are westerly. Now, we name winds by the direction from which they come, not the direction they blow, because obviously a westerly wind actually blows east, okay? We call it a westerly because it originates from the west. So winds are always named from the direction of their origin. All right, questions there? Okay, so it's just kind of another diagram of that. Okay, we can't really see that this is going on within the Earth's atmosphere because the Earth's atmosphere is transparent. Okay, we can see the movement of clouds. Like if you ever watch, like when they're showing like a hurricane's path on the Weather Channel or something like that. Okay, hurricanes, at least in the western part of the world, always follow a similar path. That is that they come in from the ocean like this, and then they run into the land and they kind of move up along the land, and then they go back out to sea to die, okay, as they make the transition from the easterly flow to the westerly flow, and they lose energy. Okay, so that's generally the way that they go. But other than the movement of clouds, which isn't always going to be consistent, okay, it's hard to see that mechanism going on within the Earth's atmosphere. Okay? But we have seen it, and we can see it really clearly if you look at other planets in our solar system, particularly the gas giants, Jupiter in particular. Okay? Jupiter's atmosphere is a roiling kind of patterned mechanism by which we can see these layers. Okay, we can actually, Jupiter has more because it's bigger. Okay, but we can see these layers of easterly flow, westerly flow, okay, and easterly flow much more clearly on there because we can see the movement of the cloud layers and things like that. I'll show you a video of it here in a bit. Okay, but this is obviously the mechanism, okay, by which it happens everywhere. Okay, it's a thermodynamics thing. It's just a matter of energy having to move by convection. Okay, everybody all right with that? Now, is this pattern always fixed and always look exactly like this? No, but it generally looks like this. Okay, obviously there are seasonal changes, okay, that can occur when it's summertime, okay, and the Earth's tilted this way and we're tilted towards the sun. Okay, those layers are obviously in slightly different places. Okay, at least, well, not so much different places as the Earth is tilted, but the atmosphere is still kind of doing this, so it feels like they're in slightly different places. Okay, when we're tilted this way, okay, well, we're definitely way more into the westerly trend, which is why we typically get way more Chinooks when? Winter. You almost never feel them in the summertime. Okay, because in the summertime, we're actually going to be tilted kind of lower in that belt, whereas here we're going to be tilted more into the middle of that belt. Okay, in the fall and in the spring, we're kind of near the top edge of it. Okay. Okay. So the Coriolis effect is the next thing I'll show you this, then I'll talk about the Coriolis effect. So you can see, okay, because Jupiter's atmosphere is colored and opaque, we can see the layers a lot better. And you can see almost like definitive lines here, okay, within the atmosphere of Jupiter, okay, that show us those. But the good thing about Jupiter is we've sent lots of spacecraft there, and we have lots of video of the movements of the atmosphere as Jupiter rotates. Now, part of the reason that these are, obviously it's the nature of the atmosphere of Jupiter, it's opaque, but also that Jupiter spins really fast. Okay, one complete rotation of Jupiter, which is way bigger than Earth, takes like 10.5 hours. Okay, so it spins way faster, right? So that spinning effect of the planet itself causes greater winds to occur. Obviously, it's further away and doesn't receive as much energy from the sun, okay, but it's still being driven by the same ideas, okay? Also, its atmosphere is made of hydrogen, which is way lighter than the gases that our atmosphere is made out of, so those movements are more obvious. Right, so I'll show you those. You'll have to excuse the really cheesy, like, computer voice narration that goes on. And this is terrible. Okay, but we're just going to look at the one part here. Okay, so the Coriolis effect is this movement of the air while the Earth moves underneath. Okay, so it's causing those prevailing winds by working in concert with convection, rotation of the Earth, okay, all of that kind of stuff. Right? So we already know that the equator obviously gets more solar radiation than other parts of the Earth. Okay, we looked at that the other day. That's why latitude is a factor that affects climate. All right, so that tends to make air move directly north and directly south, trying to obey the laws of thermodynamics. Yes, there's some horizontal motion, but it's for all intents and purposes strictly vertical. Okay, now the Earth is rotating, so winds get deflected either left or right. Okay, and that's the Coriolis effect. Okay, that's the deflection of any object from a straight line path by the rotation of the Earth. Now, it's not a true deflection. That stuff's actually moving north and south, but on the surface of the Earth, our perception of that is not that way. Okay, we're moving through it. So in that way, it is like sticking your head out the window of a moving car. Not that you should do that because it's not safe, but if you did, okay, you'd feel the wind going past you. It doesn't mean it's windy outside. It means you're moving through the air at a high rate of speed. Okay, well, it's similar to that when we're standing on the Earth's surface, rotating through air that's already moving in a different direction. Okay, like for example, do you notice the wind as much if you're walking with it? No, but if you walk into it, you notice it a lot more. Okay, so that air is moving, we're moving into it. Okay, it's kind of a cross thing, so we feel that deflection. Okay, so what we see here on this diagram is that this is the intended path, or this is the path that the winds are following, but because the Earth rotated underneath it, okay, this is where the winds actually end up, is over here. Okay, so it's missed. Right. So the Coriolis effect can affect that kind of stuff, and it has to be taken into account when you're, navigating the Earth in a plane. Okay, the Coriolis effect has to be taken into account. Incredibly long shots with a rifle. Okay, the Coriolis effect has to be taken into account. The Earth rotates under the bullet if it's in the air long enough. Okay, not like less than, let's say, 1.5 kilometers. It probably wouldn't matter much, but anything more than 1.5 kilometers, anything more than a mile, okay, then the Earth rotates underneath that projectile, right? So that would have to be taken into account. Okay, questions there? Everybody's good with what the Coriolis effect is? Because that's one that always comes up in written response questions as well when I ask you to explain how prevailing winds happen. Okay, the Coriolis effect is something that has to get worked into that. Okay, prevailing winds are convection, they're the Coriolis effect, they're thermodynamics, okay, they're all that kind of stuff. All right, so I want you guys to write down and answer these questions. I'm going to give you a few minutes to work on those. We'll go through them, and then I'm going to talk about specific heat capacity, which is the next thing here. Okay, so let's have a look at these questions here. So we want to, what's the effect of unequal distribution of solar or thermal energy on the Earth, on the temperature of the atmosphere? All right, well, where gets the most energy? The equator. All right. Second law of thermodynamics says that can't all stay there. The energy has to be transferred from hot to cold. Right. So what we see is because there's unequal distribution, the atmosphere has to move in order to equalize that unequal distribution. That movement is convection, which we call wind within the Earth's atmosphere. Okay. Use both terms when you're describing that on a test. Okay, the second law of thermodynamics says that energy has to be distributed, okay, and flow from hot to cold. Convection is the mechanism by which that's going to happen. We're going to call that convection, that movement of air, wind. Okay, everybody all right with that? Okay. Now, the other part of that unequal distribution is that there's also latent heat that's got to move. Okay, there's latent heat that's being put into the atmosphere, okay, as water vapor near the equator. That's got to move as well, and it's going to be carried by that same convective wind mechanism. It's going to move that warm, moist air from the equator to more northerly or southerly parts of the world, okay, and then that stuff will condense, transferring its moisture there. The path of that stuff can be altered by this, by the jet streams. Okay, the path of those air masses and things like that can be altered sometimes, okay, by the location and movement of the jet stream. All right, explain how the Coriolis effect influences the direction of winds in the northern hemisphere. All right, so near the equator, Hot air is rising, cool air is kind of moving in to replace it, and the Earth is rotating under it. So near the Earth's surface, okay, the wind is moving from north to south, okay, but because the Earth is spinning under it, it gets deflected like this, and near the equator, we perceive that to be an easterly or northeasterly flow of prevailing wind. So most of the time near the equator, the winds are going to be prevailingly from the east to northeast, right? When we're further up, okay, wind is trying to move from south to north. The Earth rotates underneath it, causing it to be deflected the other way, okay, giving us a westerly flow of wind. Okay, so it's a combination of convections occurring, air moving near the surface appears to be deflected because we're moving through it as it does something else. Okay, what are the trade winds? Where do they occur? Well, we just talked about them, okay, near the equator, okay, there are easterly winds called the trade winds, okay, so they happen at the equator. All right, and what are the jet streams? Okay, what's a jet stream? High altitude, high speed wind, okay, that can alter the path of air masses, okay, containing water vapor, right? Basically, the jet stream is what causes changes in weather. If there was no jet stream, weather would be consistent all the time. And but because the jet stream's shape, position, location, whatever, change on Earth all the time, okay, that causes different air masses to be moved into our area, different changes in pressure, temperature, all of that kind of stuff. It's basically the cause of changing weather. Right? The more influenced by the jet stream your area is, the more often your weather changes. We just happen to be in a place that's kind of like that. All right? The jet stream, because it's high altitude, we don't feel it. Okay, not here anyway. Right? But if you were on top of a really tall mountain, like let's say Everest, K2, or any of the really big peaks on Earth, the jet stream is something you need to worry about. What can happen if the jet stream passes over the top of one of those mountains? It can knock you off, yeah, but it causes a rapid change in weather. All right, so if you're climbing, okay, and what climbers will often look for is they will look at all the surrounding peaks. If they start to see what's called spin drift, okay, which is they see coming off the tops of mountains, wind being blown or snow being blown off the top of them and spinning like this, they know that the jet stream is moving. Okay, now climbing mountains is a lot different than it used to be. Obviously, they have satellite weather and things like that that can tell them these things a bit as well. Okay, but that's one of the signals that either you've got to be well planned, get to the top and get back down, or that you need to stop your attempt because you could get trapped up there when the jet stream passes over. It will cause a radical drop in temperature. It will cause a radical increase in wind speed. We're talking hundreds of kilometers an hour, okay? Like it could be 120 kilometers an hour in a place where it's already minus 40 degrees, okay? Imagine the wind chill, right? You would not likely survive those conditions, and that's what gets a lot of people when they climb those mountains is, I got to get to the top. I came all this way. I got to get to the top. And then they don't make it back down because the weather changes on their way back down and they get trapped. Okay, so that's something to think about. Okay, the jet stream can be felt on certain places on Earth, and it's a very wild mechanism. It has a lot of energy, which is why it has such a big role to play in changing weather. Okay. All right, any other questions on this stuff? Okay.